There's a pretty standard statement about friction that you'll come across. First of all, just clarify, friction is a force. I'm sure you're all familiar with that. And the phrase that's usually used is the idea it's a force which opposes motion. Now, what that means, to unpack it a wee bit, if an object is at rest, it tries to keep it that way. I.e., if you try to push it, friction will act in the opposite direction. Or if an object is moving, it tries to slow it down. Or another way of saying that, the opposes idea is basically similar to the word opposite. Always acts in the opposite direction. Either to a force if you're trying to get something moving, or if something's already moving, then friction will just act in the opposite direction to what the object is moving. The other thing that's important about friction, it increases when objects go faster. And lastly, the technical phrase here, and we'll come back and do this when we do the energy chapters, but it converts kinetic energy into heat energy. What everyday word might you use instead of kinetic when you're talking about kinetic energy? Movement energy. Okay, and 19 is just about looking at situations of high friction, situations of low friction. When we want to slow an object down, one way of doing that, not the only way, we can increase friction. E.g., car brakes now notice they don't actually rub against the tyre, they rub against the wheel. That's kind of common misconception. Right, and that's what slows the car down. When we want an object to go faster, we can decrease friction if possible. And deliberately, if we think of a car example again, because I want to emphasize that if you're given an example, you can't just say a car, because there are aspects of a car where you want to increase friction and aspects of a car where you want to reduce friction. Can you think of an example of reducing friction in a car and you want it to go faster? So for example, a car is shaped aerodynamically. Another word that means the same sort of thing is streamlined. And that enables. So we've already mentioned that friction is affected by speed, by material, right? So we talked about using different materials, so different tyre materials, different materials in the grips of your shoe. We mentioned the idea of the area that's rubbing together. Okay, actually I should put and rather than comma. And shape. 21. Mass is the amount of matter in an object. It is measured in kilograms, which is a bit unusual because in most units in physics we get rid of k's and stuff like that. The standard unit of distance is meters, not kilometres. But the standard unit of mass is kilogram. And you just watch, if you do chemistry, they use their standard unit pretty much as grams. Right? But for physics, it's kilograms. And here's a kind of key idea. It doesn't depend on where you are in the universe. Okay, so if you take an object and move it from the Earth to Mars to the Moon to Jupiter, it will still have the same amount of matter, so it will still have the same mass. And you're probably used to talking about your weight being in stones and pounds rather than your mass. Okay, so you've got to kind of unlearn a wee bit of what the words that you're used to in everyday life. But that's our definition of mass. Now there's a couple of ways of writing what we mean by weight. Right? They all mean the same thing, but just in case you see it written in different ways. But weight is the gravitational, and I'll use the word force, but you quite often see it written as pull. And I'll put from the nearest planet, but it could be from a moon or from a star as well. The correct term would actually be from the nearest celestial body, but I think that might be a bit confusing. And because it's a force, it is measured in newtons. And hopefully fairly obviously, because it's the gravitational force from the nearest planet, if you go to a different planet, you're going to have different gravitational forces. So it does depend on where you are in the universe. If you're not near any planet, what would your weight be? 0. Okay. And it seems a wee bit bizarre to define this first, but we'll do the formula in a wee second anyway. Now, a lot of people mix up weight and gravitational field strength. You need to spend a wee bit of time memorising what they mean. Gravitational field strength isn't any old weight, it's a weight specifically of 1 kilogram. And then when we see the next one, that enables us to write a formula. If you know what the weight of 1 kilogram is on a planet, and you've got 15 kilograms, well, you just multiply it by 15. Now, you're not expected to memorize any gravitational field strength values. You're given them in a table. Maybe worth pointing out, though, at this stage that we take G on Earth now to be 9.8. Right, in first year, we just approximated it to 10. And 22 is the formula. W equals mg. Remind ourselves what all the symbols stand for. Right, and because gravitational field strength is a weight for every kilogram, its units are newtons per kilogram, right, or nkg minus 1. Remember, the minus 1 means per. Okay, well, you've obviously done a sheet of examples, but just give you a worked example for your notes. Okay, so if my mass is 70 kilograms, what would my weight be on Jupiter? Standard problem solving technique, and I go through this question, I only have one number in the question. So I still go through my standard problem solving technique. Question tells me mass, it asks me weight. But then when you're thinking about formula, which formula links mass and weight together, then you're thinking, well, I'm actually missing G, and hopefully that's then enough of a prompt to say, I need to go and look up the table for G. In an exam, that table will be in the inside of the front cover. Okay, so even getting used to that fact, you just go and look up the table on the inside of the front cover. So from the data sheet, G is 26.4 newtons per kilogram. And write out the formula, it's an easy one, that's no reorganising. And get your calculator out. And it's 1,848 newtons. Strictly speaking, remember significant figures. Try and give it to 3 significant figures. So it should really be rounded up to 1,850 newtons.